So in this video, we're going to use related rates to find the rate at which a balloon volume is changing. So here's the example. It says a spherical balloon is being filled with helium. When the radius of the balloon is 6 centimeters, the radius is increasing at a rate of 2 centimeters per second. What is the rate of change of the balloon volume at that moment? So we're going to want to find the rate of change of a balloon volume. We're being asked to find dV dt. This is the unknown. So question mark. We know that we're filling a spherical balloon with helium. So what we want to do is get the equation or formula for the volume of a sphere. So the volume of a sphere as a function of the sphere's radius is equal to 4/3 pi r cubed. So there's the volume of a sphere. So to find the rate of change dV dt, here I know that I have volume as a function of radius. So related rates, implicit differentiation, tells me that to get dV dt, I'm going to need to find dV dr, the rate of change of volume with respect to radius, and then I'm going to need to multiply that by dr dt to get dV dt. So I want to write down the rest of the information that I have. So I came up with my formula for balloon volume, or volume of a sphere. I'm being told that when the radius is 6 centimeters, that the radius is increasing. So the radius is increasing at 2 centimeters per second. So I'm being told when r is 6, dr dt, the rate of change of the radius with respect to time, is 2 centimeters per second. And now I've extracted everything from the paragraph that I can get. So to find dV dt, we first need to take dV dr. So take the derivative with respect to the radius. So the derivative is going to be 4/3 pi. And then we need to take the derivative of the cubing function. So we're going to get 3r squared from there. So there is our dV dr. But we need to multiply that using implicit differentiation. We have the function r inside of the squaring function. So applying the chain rule using implicit differentiation, we're going to multiply that by dr dt. So now I have dV dr times dr dt. And that is the time derivative of the volume of the spherical balloon. Now I'm being asked to find the rate of change of that volume when the radius is at a specific moment in time, when the radius is 6 centimeters, and the rate of change of the radius is 2. So now it's just a matter of plugging that information. Actually, I should simplify this first. So dV dt equals, I can cancel those 3's, and that's going to give me 4 pi r squared times dr dt, and now it's just a matter of plugging in a radius of 2 and replacing dr dt with the 2 centimeters per second and the radius r with the 6 centimeters. So when the radius is 6, then dV dt is going to be 4 pi times 6 squared times dr dt is equal to 2 centimeters per second. And now it's just a matter of simplifying things. We have 8 times 36 pi, which is going to be 240 plus 48 times pi, which is just going to be 288 pi centimeters per second. Whoops, not centimeters. This is a volume. We're after the rate of change of a volume, so it's actually going to be centimeters cubed per second because it's a measure of volume change.